We are going to begin our discussion of the second part of Unit 1, which is to discuss rational functions. Pre-calc is kind of based on doing two things. Number one, it's doing more study of a lot of different kinds of functions so that when you go to calculus, you can work with those functions with some knowledge. So that's number one. And the other part of pre-calc is learning trigonometry to assist you, because you definitely need to know trigonometry as a part of a theoretical calculus. And applied calculus, we don't use as much trig. We do a very little bit of trig. In regular AP calculus, or if you take a non-business, because that's what applied calculus is, a non-business calculus class, you definitely use trig. So what are we doing in this class? We're talking about functions, and we're talking about trigonometry eventually. So we talked polynomial functions. Now we're going to talk rational functions. And a rational function is just a function that's the ratio of two other functions. So f of x here, where equals p of x over q of x, is a rational function where p of x and q of x are polynomials. Okay. So you take a couple polynomials, you set them up in a fraction or ratio, and you've got a rational function. Rational functions always look scary because they're fractions, and for some reason, fractions are super scary for us and we don't like them, and they make some of us just kind of like, sweat and feel crazy. But there's no reason to be afraid. A rational function is just two polynomial functions in a ratio. So we can use a lot of the things we know about polynomials to help us work with rational functions. Okay. So, let's say I do something like x squared minus 5x plus 6 over x squared. Okay. Minus 4x minus 5. That's a rational function. Is a rational function. Okay. The numerator function and the denominator function can be different degrees. They don't both have to be quadratics. You can have linears, you can have squares, you can have cubes, you can have different ones in different places, you can just have constants, you can have all different kinds of combinations. So anytime we take one polynomial and put it over another, we create a rational function. Okay. So what are we going to want to do with a rational function? Just like a polynomial function, we want to be able to talk about what the graph's going to look like, and we want to be able to create the graphs. So polynomials, we spent the first set of time sort of talking about what they looked like, because polynomials are very predictable. Rational functions are not as predictable. They're kind of more of a little pain in the butt. But we can still predict what they're going to look like through a little bit more help, and we can still create graphs. Now, new features. Things that rational functions have that polynomial functions don't. Number one, Rational functions can have holes in them. Polynomials don't have that. Polynomials are nice and smooth and connected, and it's all happy, and we just connect the dots and the world is good. Rational functions have holes, can have holes. And if you're like, what do you mean a hole? I mean, it can look like a line, la 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 la, boop. And you all of a sudden have a spot where the function becomes undefined. Okay? We need to know where those things are because we're going to have to show them on the graph. They don't really show up when we graph them in technology things. If you try to graph, let me show you this, a rational function, or when you do graph a rational function, let me show it. Right, but then do something like this. Oh, come on, stupid thing. Oh, why do you hate me? Oh, why do you hate me? Oh, God. Clearly, I am being an idiot. There we go. Since I can't seem to do it any other way. Okay. So, there's a rational function. Now, this rational function looks like a nice little happy line. Everybody's all good. But when you scroll on it and you look at the ordered pairs, whoa, wait a minute. If you pass it too fast, you find there's a hole in that function. It doesn't show up when you just look at it. And the same thing happens on your TI 83s or 84s. So we're not going to know, even if we did just type the function in, we're not going to necessarily know that there was a hole. We have to be able to look for it. All right, so that's the one of the new features of a rational function. The other one, vertical asymptotes. That is a horrible writing of the word asymptote. Let me write it again. A-S-Y, asymptotes. Vertical asymptotes. Now, here's a vertical asymptote. You've got that kind of vertical line. And it breaks the graph into two branches a lot of times. And what happens is it runs up against the vertical asymptote and it gets infinitely close to the asymptote but doesn't cross it. So it kind of is like a wall that the function runs up against on either side. And it's another place where the function gets undefined. The function can get undefined just at one little teeny tiny spot or at a whole bunch of spots. It's kind of like there's a whole bunch of holes that kind of gang up together, if you want to think about it that way, and make like a whole line of undefinedness that makes a whole barrier. Why didn't we talk about these a couple weeks ago? Because polynomials don't have these. But rational functions do. And the thing that makes the rational function have all these weirdness are places where the denominator equals 0. Because rational functions have a denominator, and a denominator equaling 0 means dividing by 0, and dividing by 0 is not defined mathematically. Having a function where something gets divided by 0 means the function kind of blows up right there. It goes like, woo, I can't be a function. I can't work there. Woo. Or, man, I can't work for a whole bunch of things. Denominator function equaling 0 is going to be the first thing we're going to have to care about. Because where the denominator equals 0 makes all this messy stuff. Holes and vertical asymptotes. And all this messy stuff is the stuff that's going to be something we're going to have to worry about when we draw our graphs. Our graphs are going to have holes and vertical asymptotes and be in pieces. It's going to be a little bit tougher to connect the dots. We'll still be able to do it. It just, we have to watch for kind of all these weird things. So bottom line, here's a rational function. The first thing I need to worry about is the numbers that make the denominator 0. The numbers that make the denominator 0 potentially are going to create holes and vertical asymptotes. Now, how do you know which ones create which? We'll get there. That's coming. For now, we just have to pay attention to, I need to know where this equals 0, which means in a lot of cases, I got to do factoring. So, let's start with a few rational functions. Let's figure out where the denominator equals 0. And we're actually going to use those 0 numbers to describe the domain of the function. All right, so let's find where the denominator equals 0. All right, so here's our first one. This plus 2 over there. Okay. So notice right away, I'm going to focus on the denominator. I'm going to care about the numerator stuff, but I'm not going to care about it right away. So x squared minus 8x plus 12 equals 0 is what I want to be thinking about. And if you're like, well, wait, like what's different about figuring out where the denominator equals 0 and finding the roots of a polynomial? There's no difference. These aren't roots. They're trouble spots. Okay. But it's the exact same kind of process. It's the exact same thoughts we thought about when we wanted roots of a polynomial. Zeros of a polynomial in this case, just the polynomials in a denominator, making this scary thing called a rational function. So x minus 6 equals 0, x equals 6, x minus 2 equals 0, x equals 2. Everybody good? Yeah. Okay. So what are we going to do with these first? Well, eventually we're going to want to figure out if they're wholes or vertical asymptotes, and we're going to figure out how to put them on the graph. But what I'm going to do right now is I'm just going to use them to make something called the domain. Right? The domain, okay, if you think of it, and I know this is not the first time you've heard this, all the good or working x values for a function. Some function graphs are just individual points, and so the domain is just individual x numbers. Some functions have all the real numbers as the domain, negative infinity to infinity. Polynomials, negative infinity to infinity domain. All the x numbers for a polynomial are good. And if you're saying, well, what do you mean good? I mean, they make the function work. And these denominator zeros are actually bad guys. So when I write my domain, I'm going to say I'm good from negative infinity up to, actually I lied, not up to 2. So, oh. Hi. I'm good. Nope. Sorry. See, I'm polite. I didn't make a face till he wasn't looking at me. Okay. Here we go. So, this is how I would describe the domain for this function, for this rational function. Basically, all x's from negative infinity to infinity except x equals 2 and x equals 6. So this is one way to write it. That's one way to say, hey, look, it's all of these numbers. All the numbers from negative infinity to 2 and all the numbers from 2 to 6 and all the numbers from 6 to infinity. Those are good pieces, good x numbers for my function. And this is what this means. This then also tells us my function graph is going to be in 3 sections. And those sections are going to be divided by either wholes or vertical asymptotes. So wholes and vertical asymptotes, the bad guys from the denominator, break up our domain. Describing the domain helps us describe what we're going to expect to see when we see the graph. A 3-piece domain like this, I'm expecting to see 3 sections when I graph this. I'm going to see a section for the x's from negative infinity to 2. I'm going to see a section from 2 to 6. I'm going to see a section from 6 to infinity. Now, what breaks these sections apart? They might be vertical asymptotes. You might get 2 of these scenarios. You might get a couple of these scenarios, and you might get 1 of each. These are different ways the function gets broken into pieces. Wholes, vertical asymptotes. From the denominator zeros. Now, are we going to care about the numerator? Absolutely. We are ultimately going to care about it. But for today, our focus is just bad guys for the denominator, whole and asymptote creators, i.e. breaks in the domain. So I'm going to ask you to do exactly what I did on that last problem for these two. Find the zeros of the denominator and use those to create the domain or write the domain. Okay. So that's number 2. Write him in another color. Okay. All right, see if you can find the domain for each of these. And remember, that means finding the zeros of the denominator and letting those zeros describe how you're going to how it's going to split up, what x values you're going to drop out. Pull that down a little bit. Okay. That's a lot of information. Okay. Oh, okay. Great. Oops. Exciting. Okay. Go back to my problems. There they are. Okay. All right, so for now, we are focusing exclusively on the denominators. They are both, our denominators are going to be polynomials. If they're a polynomial that doesn't factor, it makes everything a lot more difficult, obviously. So we're going to focus on rational functions with pretty nice polynomial denominators. I was thinking the D word. I was trying to say derivative. But we will look at a few that are weird. So checking out x cubed minus 5x squared minus 6x. Factoring out an x. Okay. And then the remaining quadratic with a minus 6 and a plus 1. So x equals 0, x equals 6, x equals -1 are the zeros of the denominator. So when I write my domain, and this is the part that's tough, and you might do this, you might want to organize them on a number line for yourself. So if you were on a number line, oh, that's a horrible looking number line. You know, -1 would be first, and then 0, and then 6. So my domain is -infinity to -1, -1 to 0, 0 to 6, and 6 to infinity. The bigger degree denominator you have, the more potential locations you have for problems, for weirdness, for holes and vertical asymptotes. So this graph would be in 4 pieces. A section of the graph from -infinity to -1, another one from 1 to 0. Oh, not 1 to 0, excuse me. -1 to 0, 0 to 6, and 6 to infinity. Now, whether these disruption points are going to be holes or vertical asymptotes, we will address that in our next lesson. Questions, problems with those particular values? All right, this guy. Factors of 6 that add up to -5. We're going to need -3 and -2, 2 negatives. I would probably put the -3 first. So a 3x out of these two leaves me with x minus 1. If I do an x minus 1 back here so that we get the match, this would have to be a -2. So 3x minus 2 and x minus 1 would be the factors. Make this a little neater up here. So 6 and -5, so -3, -2. So the fun numbers are 2/3 and 1. So my domain goes from -infinity to 2/3, and then from 2/3 to 1, and then from 1 to infinity. That's a horrible looking infinity. Try writing that again. Let me write that again. -infinity to 2/3, and 2/3 to 1, and 1 to infinity. That's my domain. Once again, the domain helps us get focused on how many pieces our graph is going to have. And then once we figure that out, we'll figure out what the breaks are between the pieces, whether the 2/3 is going to be a vertical asymptote or a hole, whether the one is going to be a vertical asymptote or a hole, and then filling in the graph around that. Okay. We will need x-intercepts. X-intercepts are going to come from the numerator. We'll figure out where the holes are. We'll figure out where the vertical asymptotes are from this. We'll figure out where the roots are from the numerator. And then we'll figure out end behavior. And then we'll be able to make the graph. All right, so your responsibility will be to practice this after your test on Monday.